Okay, exam 2, we have 3 weeks left of class. For those of you taking the exam remotely, it's tomorrow. You can either start at noon to 12:45, or if you have an appointment at a different time, that's okay too. But if you don't have an appointment, you're going to start between noon and 12:45. Exam 2 will be in Frankie on Wednesday, 4:36, and we'll start Lab 6 on Wednesday also. Lab 5 will be due this Friday. And then we have 2 weeks left of class. We'll finish Lab 6. Last week of lab, there's no lab, but you may have a lab due. Your lab will probably be due Friday, April 23rd. It's just not on here. Final exam is Monday, April 26th for everybody from 3 to 5 p.m. It will either be remotely or in Zoom. Yeah, just let me know in advance if you're planning on doing it remotely so I don't get too terribly confused and print 20 extra exams. Okay, so this is called exam 2 review because wait. Oh, it is exam 2 review. Never mind. I fixed that. 4 sheets of paper, anything you want on it. The 2 sheets from exam 1 and 2, make sure you have those for the final. You get 2 new sheets for this one, basically. You can use your calculators, other electronic devices. That's kind of old. There is one multiple choice problem, which is probably the one people do worst on the exam, in 3 parts. It's worth 6 points. 6 problems worth a total of 100 points and 6 points of extra credit. Just answer the extra credit problems. If you answer them, you get credit for them, basically. On the front page of the exam, these numbers are printed. Use these. Don't use other numbers. We're going to use VT equals 25.9 millivolts for this exam. NI, we're going to use 1.5 times 10 to the 10th. And Q is always the same. The rest of them vary. So those are available. Any problem, if you need one of those numbers, just look at the front of the exam. And VT is already calculated for you. Stuff from EE280, I'll expect you to know. Ohm's law, KVL, KCL, parallel voltages. Things that are in parallel have the same voltage. Things that are in series have the same current. Engineering notation, know those multipliers from EXA to ATO. They show up in the calculations occasionally, some of them more so than others. Be able to use current and voltage dividers. Node voltage method as a last resort, it always works. I took that problem off the exam because I just figured with all the, since there's more volume of information on this one, you didn't need that problem. It was a diode problem. It stumped Jack. You don't know Jack. Ideal voltage and current sources. So if I have an ideal voltage source, if you see a voltage source on your exam, assume it's ideal. And this is, let's say this is 5 volts. And put a bunch of resistors in parallel across it. We know that this current source will produce whatever current we need to keep those parallel resistors having the same voltages. So this will be 5 volts also, and this will be 5 volts. And the current will be determined by the values of the resistors I put across there. Now, ideal current sources, there's no way to panic, students. I know better than to put a current source on the exam. Let's look at a simple example here. I've got a 5-volt voltage supply that's providing power to a, let's call it 100 nanoamps. Why not? 100 nanoamps going into a 10 mega ohm resistor. This is coming from experience, I see people who have trouble with this. The first thing you don't know is you don't know the voltage here. It's not 5 volts, I can tell you that much. It's going to be whatever voltage this current source is going to need to drop to get the current going through it. Since the 100 nanoamp and the 10 megohm are in series, the 10 megohm will also see 100 nanoamps, and the voltage across it is going to be 100 nano times 10 meg. That you do know. Resistors you can rely on. What the voltage drop is across a current source, or what the current supplied by a voltage source is, you have no information until you start looking at those resistors and diodes. Since this voltage here is referenced to ground, Vout will also equal VR. If it was referenced to, like, oh, let's just make this the bane of everybody's existence. How bad can I make this? Oh, I just lost my, put it back. Let's make this a negative 5 volt source. One of my favorite things to do. If it's negative 5 volts, then Vout does not equal VR. Vout will equal negative 5 volts plus the voltage across that resistor, so plus VR. Okay, just some really basic stuff I wish you learned in 188. I occasionally threaten to go back and rewrite 188, but they'll never give me the time. They'll never give me credit for doing it, let's put it that way. I could make the time, but I'm not going to do it unless they actually give me credit for it. So diodes was chapter 4 in Cedra, homework 7, and the diode slides. Generally, for most calculations, you use that 0.7 of a volt offset model. A lot of you realized in lab when you actually did a better calculation using multisim, it's not exactly 0.7 of a volt, but it was in the ballpark, and it gave you a reasonable answer. If you're using exact values of current, the best exact value hand calculation you can get in a reasonable amount of time is to use this. I equals IS e to the VD over VT. VT is a number written on the front page of your exam, -1. So be able to do that calculation. We looked at some circuits, rectifiers, limiters, and some other diode circuits. We're not, okay, we'll talk about that in a minute. Semiconductor physics, this was homework 8. The formulas on page 159 and 60 in Cedra Smith's 6th edition, or use the index and find that there's a table in the diode chapter. There's some of the equations are in the slides. I would focus on getting on your formula sheet the formulas you used in the homework. Not all the formulas in the slides, but focus on the ones that I actually made you do in the homework. Make sure any links that you're using are converted to centimeters, and remember that any answers you get that are links, like the width of the depletion region, will come out in centimeters. You could get something when you calculate the depletion width that looks like 10 to the -6th. That's not micrometers. That's 10 to the -6 centimeters, which is 10 to the -8 meters, which is 10 nanometers. Don't leave it in the form of 10 to the -6 centimeters unless you want to get a smart alecky comment on your exam and maybe a few points taken off. Good answers for that would be 10 nanometers. 100 angstroms would just overjoy me. An angstrom is just 1/10 of a nanometer. 10 to the 8, and remember in your calculations, 10 to the 18th, when you punch them into your calculator, you punch it in as 1 times 10 to the 18th, not 10 times 10 to the 18th. That's the cause for a lot of calculation problems that I saw. When you're making your exam sheet, I would go and see what formulas and information did you need to solve homework 8. When you get that down on a piece of paper, that will really help you out. Approximately 1/4 of the exam is semiconductor physics, 1/4 is diodes, and the other half is all MOSFETs. Okay, we're going to skip this one because I didn't put it on the exam. There's something sort of like this on the exam, but not exactly. Circuit analysis. First thing we got to do is figure out the DC values. So this is kind of like our small signal model for diode. We figure out the DC values, and let's just do that part because that's what I focused on for the exam. That's usually enough to throw you guys off. So the first thing I look at this, I don't know the voltage drop across this current source. That's a big question mark. And I don't know the voltage drop across this current source. I just know it's going to be supplying current. So that doesn't help me with the voltages. This current source here, since it's in series with D1, tells me that the current for D1 has got to be 2 milliamps. So that I can get pretty much from inspection because it's in series with a current source. Oh, I can even do this one over here. I can use KCL. Let's just go straight to KCL. The current going through here is 2 milliamps. The current coming in is 10 milliamps. So the current going out has to be 8 milliamps. And that's just an application of KCL. So we got our currents pretty easily. The next thing I have to do is figure out the voltages. So I don't know the voltages across the current sources. I'm not even going to try to guess. I know for certain that this voltage here is not 5 volts. And I know this one is not -5 volts. I'm going to look at the diodes because I can assume the diodes are on because the current's going in the right direction to turn those diodes on, and the voltages is the right polarity. So I'm going to say the diodes are on. And if I come up with something ridiculous, I will change my mind on that. Okay, so if the diode is on, then I have 0.7 of a volt across D2 and 0.7 and positive going that way, 0.7 of a volt across D1, positive going that way. Now, since D2 is referenced to ground, I can say the voltage here is going to be 0.7 of a volt. And when I drop 0.7 of a volt across D1, because the polarity is going the other way, this is going to come out to be 0 volts. You cannot determine voltages by looking at current sources. At least half of you might figure that out. Okay, good. We need this, like, that's what I really need to do. I need to write a 1-hour class that is EE180 boot camp, kind of like the CS skills classes, the engineering skills classes. Again, they're not going to give me credit for doing that, so I'm not going to do it. Okay. 11. Where are we at? The ideal diode equation. So if I look at this equation here, I can solve it for VT. That's all I've done here. I take I divide it by IS. Then I have to add 1, put that in parentheses, because that is going to equal E to the VD over VT. To get VD over VT, I have to take the ln of both sides. So I get the ln of I over IS plus 1 equals BD over BT. So I just multiply this by BT. I have an expression for BD. I could also solve that equation for IS. It would be I over the exponent, over what's in parentheses. So if you know 2 out of 3 things in that equation, IS is usually a number that's on the data sheet, or you're calculating it, or you're measuring it from using this curve. VT is on the front page of the exam, and your real variables are IS, VD, and I. Can you solve for the other one? So if I have VD equals 1 volt, and I'm given VT in this problem is 25 millivolts, and I don't go to the front page and calculate, I look up the 25.9, because I have a slightly different temperature. I have a low, this is operating at a lower temperature. Could you calculate I? And I would just be 10 nano times e to the 1 over 25 milli, and that whole thing is minus 1. Do not underestimate my ability to twist that equation. You can, Donovan, you can print out the exam and do your work on the printed out exam, or you can do your exam on separate paper and scan that to me. The thing that you have to be able to do is scan your work. Whether you have a printer or not is optional. Okay. These are important constants, and they are on the front page of the exam. I may not have K on there, because I may just have what you would use K for would be calculating VT. VT is on the front page of the exam. T is always in Kelvin, and 300 Kelvin is about room temperature. Is with a sloppy ballpark number people always use. Remember to put your lengths in centimeters. If I have an area in centimeters, if I have an area in micrometers squared, I need to convert that into centimeters squared. Here's my list of equations I compiled. It's almost complete for what you need on the exam. Again, I would go back and look at what you needed for homework 8. This is the big one right here. This is the mass action law. Remember that Na is usually given because that's how many atoms I've bombarded my crystal with. I know that. Na is the number of acceptor atoms, so that's going to approximately equal P. And I hope I didn't do this to you guys this time. And D is going to approximately equal N. So I put so many atoms in that have an extra electron on them, I'm going to get approximately that number of extra electrons in there. Probably the most important equation. There's the equation for B0. Here's the one for W. Yes, you're going to have to calculate some of this stuff. Again, I'm not going to make it as long as the entire homework 8 on your exam. So I'm going to pick things that you can calculate easily that hopefully don't depend so much on the previous calculation. I think you have to do your entire semiconductor physics thing is calculating 1, 2, 3, 4 things. And one of them is really simple. And the second one's fairly simple. The third and the fourth one are not quite as simple. Okay. So, right. And this is solved in the slides, and I'm going to run out of time otherwise. You were given all this stuff. The biggest thing we'd have to worry about here, the gotcha on this one, is the areas given in micrometers squared. So 200 micrometers squared, we got to convert that into centimeters squared. A micrometer on the bottom, so it cancels out. a centimeter on the top. Micrometer, they're off by 10 to the 4th. There's 10 to the 4th centimeters per micrometer, and I need to square that. So this is going to become 10 to the 8. 10 to the 4th squared equals 10 to the 8. Okay, so make sure you do those conversions. When you get the answer for W, W is going to come out to be something like, most people can do these calculations, 14 except for semiconductor physics. When you get the answer for W, it's for this particular problem. You get 98.8 times 10 to the minus 6th. That is not micrometers because that is in units of centimeters. Good. Wait. There are 100 micrometers per centimeter. No, there are 10,000 or 1,000. Yes, 10 to the 4th. We need an extra 0. 10 to the 4th is got 4 zeros. 10,000. Yes. 100 micrometers per centimeter. A centimeter. Okay, there are 1,000 micrometers per millimeter. Each one of those is off by 10 to the 3. But remember, a centimeter is 10 to the minus 2 meters. And a micrometer is 10 to the minus 6 meters. So they're off by 4 zeros. Yes. There are 10 to the 4th, no, there are 10 to the 4th micrometers per centimeters. The second version of that was correct. They're 10 to the minus 4th centimeters per micrometer. Okay. One horrible thing they did to us by making our base units in centimeters. It wasn't my choice. Okay, so when I get this 98.8 times 10 to the minus 6 centimeters, I've got to convert that into reasonable units. This is just like, I take points off and write smart alecky things on your paper. So first thing I could do is convert it to meters, because that would probably be the easiest thing to do. Into meters, it would be 10 to the minus 8, because it's off meters by 2, 10 to the minus 8 meters. And then we could say, oh, that's 988 nanometers, or it's the same thing as 0.988 micrometers. Either one of those is right. Any other thing like this, this is a -1, this is a -1. Okay. If you say it's 98.8 micrometers, I'd probably take off -2 because you didn't realize what units your answer was in. Okay, yeah, this was really evil. I'm not going to do that one again. That's the one Jack got mad at me about. I don't have enough points on this exam to make up for that, but it was a diode problem and it involved node voltage method. Let me just put it that way. Okay, so now on to the second part of the exam. Yay. MOSFETs. This is the planar technology that's in the Cedar-Smith book. This is the FinFET technology they were using until about, I want to say 18 months ago. And now they're using, not this, which didn't work, this is 6 months old. They're using a wider version of this called a nano sheet. And we'll talk more, okay. Talk more about that in EE280. So here is a grade increasing opportunity already, even though you guys don't need it so much. If you do the online class evaluation, I will give you 5 points on the final exam. I will literally add 5 points to your final exam grade. Please email me the receipt. You just have a button down at the bottom that says notify instructor, and you'll get an email back that just says I checked you off. I will have a list that looks surprisingly like this, except it says course evaluation and then practice final. You will get some additional points on your final exam for doing the practice final. And then I add all those together and add that to your final exam score. Generally, the course evaluations close the Sunday at midnight before finals week. So you can't wait till the day of the final to do it. You have to do it the week before. Okay, and it is exam 4. This is the second part of the exam, and I already said that. So the point breakdown on the exam, there's 25 points for semiconductor physics, diodes, 21 points, and some of that is kind of physicsy. MOSFETs 1 and 2, so that's calculating, most important thing, what region of operation is it in, and what is the current? And what is the current with channel length modulation, and when is that important? So that is on there, that's 34 points. And the MOS digital is 20 points. Notice there's no points for MOS analog. Okay. Again, this is a condensed version of my exam 4, which is the second part of your exam 2. Okay. Anything I could have put on exam 3, diode, semiconductor physics, and MOSFETs will be on this exam. So what did we do with MOSFETs? There's the homework 9 problems, finding the DC operating point. Did I do that to you guys? Possibly. Finding the operating region. Did I do this to you? Yes. NMOS and PMOS. Can you find, given the voltage at the gate, the voltage at the drain, and the voltage at the source, are given a picture that looks like this, 1.2, 0.8, 0.2. Given a picture that looks like that, can you tell me what region of operation it's in? Not knowing, having the drain, the gate, and the source labeled. PMOS and NMOS have different rules. I really want to focus on this because I'm still seeing some problems in 380, and I want you to get this part of it down. Can you find, that's the most basic thing you can do for any transistor. When your transistor circuit's not working, it's usually because you have it in the wrong operating region. So being able to verify that is a pretty useful skill. Finding ID. Once you know the region of operation, you plug things into the formula and you got it, and we'll go over those. And can you calculate GM and little RO? Okay, what was next? CMOS digital. Okay, we did a lot of things in here. A lot of them we're going to do in the lab. The more confusing stuff we're going to do in the lab again in 380. But probably knowing that inverter circuit for CMOS would be really helpful. And being able to make any function out of a CMOS circuit. Typically, there's 3 ways I can ask this. And this is probably the problem on the exam most people will do best on, is I can give you a picture of a CMOS circuit and I ask you what the function is. Can you figure that out? We got to put a bar over the other end. I can give you a function and ask you to draw the circuit. Or I can give you a partial circuit and ask you to complete it and tell me what the function is. Noise margins, we're gonna get this is the first 2 labs in 380. And we will look at this again in 380. So I'm not so concerned about you losing that stuff here. And dynamic power is really important. That's one of the most basic things. The dynamic power basically equals the frequency you operate at, how many gigahertz your clock is, times the capacitance you have to drive, times whatever power supply you have squared. It's like the rule it's the rule that's been ruling the world for quite a while. We want to run faster, we got to lower the power. We got to lower the voltage supply to keep the power down, to keep from melting these things. This is probably where most of the focus is right here, as for points on the exam. MOSFET analog, again, we spend the entire of exam 2 and 380 on this, and I like the way I do it in 380 better, so I'm not going to be too concerned about that. But this DC operating point is important, and this is basic circuit analysis. I may hit that with a diode problem, or I don't know what I did exactly. Yeah, that's okay. What next? So we want to determine the operating region. This is how we do it. We have to look at the picture of the transistor and figure out what VGS is, what VDS is, and follow the algorithm. Or I could figure out what VGS and VGD is. Either one of those will work the same. For PMOS, I have to use this version, one of the PMOS versions. The current equations are the same for both PMOS and NMOS. You just have to be careful because the NMOS equation is going to have a heck of a lot of negative signs in it. Yeah. And the only other thing you might possibly need for this is if I give you Kn instead of Kn prime. Kn is just Kn prime W over L. So if you can figure out the operating region, you can figure out the current. Yeah. That's most of the MOSFET problems right there, condensed into one slide. And then the other trick here is you get pictures like this, and you don't know what symbol's which. Can you tell me if it's PMOS or NMOS? The ones with the arrows going into the transistor, the NEs, are all PMOS. You tell which symbol it is. This is the first part of the problem. Can you tell what NMOS, which ones are NMOS? The NMOS have the arrows going out. Arrow indicates current of direction flow. So current's flowing here, that way, it's current's flowing downhill. For the symbols, for PMOS, the gates are always the same. The one with the arrow on it is the source, or for PMOS, the source is usually up. And the one with not the arrow on it is the drain. So not the arrow on it is the drain, it has the arrow is the source. The drain and the source are flipped between PMOS and NMOS to get the direction of current all flowing down the page. So you have to be able to figure out which terminal's which, and then apply these algorithms with VGS and VDS. VT will be given, and then calculate the current. If it's in cutoff, it's 0. This is triode, and this is saturation. Okay. What else do I have to do? Am I actually going to do this quickly? Transconductance and output resistance. So the transconductance is defined by this equation. It's the change in ID with respect to VDS. And based upon our basic transistor model, this is always true. Pick the equation that you have the information for. Pick the version that you have the information for. To find the output resistance, it's 1 over lambda ID if you're given lambda. it is the early voltage, the magnitude of the early voltage, and resistance has got to come up be a positive number, over ID. So depending upon which one of those you're given, you can calculate little RO. And the basic transistor model, it's not the hybrid pi. Why this? I keep forgetting to correct that. Hybrid pi is for BJT. That's what we're doing next. This is just, let's call it the small signal model. It looks like a pi when we do the BJT model. We'll do that for the next couple of weeks after the exam. So the most basic hand model I have for my transistor, I've got a gate node here, I've got a source node here, I've got a drain node there. The gate to the source voltage is of course BGS. There's a current source that's whatever value I've calculated for GM times whatever value of BGS I have, usually left as a variable, and RO I can calculate using the above equation. Okay. So for inverters, oh yeah, that was a horrible homework, wasn't it? Calculating the VOL and all that stuff for a TTL. You had to read data sheets. We'll do a lot of that, but we'll get better at it. You'll spend most of the rest of your life as an engineer, you're going to spend as an expert shopper. You have to go out, you've got some kind of problem, and someone else has also seen that problem, and some company's selling a solution to this problem. And part of your job is to go out and find the best solution. So it involves just sitting there reading data sheets and comparing them and figuring out which one's best. And then you get to be a hero when you come up and say, look, I found this op-amp. It's 2 cents less, and it does everything we want it to. And then they calculate 2 cents times a million, and suddenly it's like real money. And then you get your bonus that quarter. My bonuses were sometimes more than my pay. And yet I left that job. To work in astronomy. So we have all this stuff for the inverter, calculating this. Again, this is something I will beat to death in EE280. So we'll see it again, not so much for this exam. The dynamic power, this one sometimes shows up in your exams in here. It's just FC VDD squared. It's kind of like the one thing that you say, like the resonant frequency is 1 over root LC, that makes people think you know what you're talking about, even when you don't. The delays, again, this is something we will see again in 380, so I'm not so worried about this as much on this exam. This I am. This is like, you go on an interview to a company that makes anything in Arizona, like Micron, which is in Boise, and Microchip, Raytheon, General Dynamics, and you're interviewing for a digital design job. They're going to ask you some weird, like, can you draw a 2-input NAND gate? And it's 4 transistors, and yes, most of my students can do that. So this I take seriously, and remember it's like about 20 points on the exam is CMOS digital. This is the key skill you need to get out of this class. So we want to figure out what the function is. Remember, our rule is for NMOS, things that are in parallel are an OR function. Things that are in series are an AND. And for PMOS, I invert that. Things that are in parallel are an AND function. Things that are in series are an OR. And I got to remember to put a bar over the whole expression. Bar at the end. Like at the end of the exam. Okay. So what we do is we look at this. We see B and C are in parallel. I always do the NMOS first because they make more sense to me. They're in parallel, so it's an OR. So I've got, yeah, we'll come back. I will be back shortly. This is slide 17. Okay, take a break.